Okay, constraint dynamics. First, I'm gonna assume everyone has done analytical mechanics in some form, be it Lagrangian first or Hamiltonian first. So I'm gonna just directly start with the Euler-Lagrange equation. So the Euler-Lagrange equation is where the curly L is the Lagrangian, full time derivative of partial L with respect to Qi dot. This we can denote as the Euler derivative set to zero. That's the Euler-Lagrange equation. Now, what I'm going to do is I'm just going to expand the full time derivative a little more. Now, people who've seen this this equation and or what happens when you expand, just bear with me. I'm trying to formally motivate the topic that we're going to talk about today. And again, I'm using the Einstein summation convention. Equals the second derivative with respect to Qi dot Qk dot Q double dot K. So I'm going to define this quantity called the Hessian, indexed by I and K, as just the second derivative of the Lagrangian with respect to these velocities. Okay, so what do we do after this? We'll see is the unique solution for the acceleration, which is Qk double dot, as a function of Qi dot and time, exists if and only if this this thing, which is the Wik, the Hessian, is invertible, because you want to sort of invert this when you're taking when you're taking this quantity to on the other side. You want to invert it, and that will only be possible if the determinant which I can denote as W is non-zero. So we can also see that Wik is actually partial with respect to Qi dot of the momentum Pi. So in other terms, we cannot solve Qi dot in terms of Pi if completely if is not invertible. So if we can't solve all the velocities and convert them into respective momenta, that just means the Legendre transformation. Uh, Legendre transformation. These are a bunch of fancy names, but the Legendre transformation is what enables us to convert from a Lagrangian mechanics perspective to a Hamiltonian mechanics, and vice versa, as long as it is invertible. In this case, we're considering the non-invertibility, and that's essentially what starts constrained dynamics. We wouldn't have considered this in an undergraduate fundamental like introduction to Hamiltonian's Lagrangians, because the systems are inherently quite easy. So what I'm going to just elaborate on this further. So let's say that there's degrees of freedom, and those are denoted by the dimension of this matrix. Call it n. So if the rank of the Hessian is R and is less than n, then by basic linear algebra, there exist n minus r null eigenvectors that will span the kernel of the Hessian. These eigenvectors I'm going to call ys of q dot. That is ys wij is 0 for s equals 1 to n minus r. Now in this expression that we have here, in this expression, I'm gonna assume that there's no explicit time dependence, so this term drops off, and I'm gonna define the quantity vi to be minus so li, the Euler derivative, is minus the Hessian plus vi set to 0. And then since we had eigenvalues, null eigenvectors, my bad, this equals 0 just implies that yis vi is also 0. And if we consider the set of these equations that are independent, we can denote them by phi s of q dot yis vi equals 0 for s going from 1 to n minus r, which I will call m, capital M. So these independent phi's are called Lagrange constraints, and they're simply born out of the fact that this Hessian, which was required to be invertible for an invertible Legendre transformation, is in this case not invertible. So this was still the Lagrangian formalism, Hamiltonian formalism. So what we do is, once we have Lagrange constraints, if you want to sort of build off from the Lagrange formalism, what you can say is you can solve for those like r momenta from from the queues, the ones you can solve, that because of the rank is R, you solve for them, and you sort of plug them in the Lagrange constraint, so that you get a constraints q comma p, where p are the momenta you could solve for, where m goes from 1 to capital M. These are called primary constraints. So let me just denote that this is Hamiltonian formalism. So let's see what's happening geometrically, because when I was reading one of the readings given to me, the initial part was kind of like a recipe that do this, do that, do this, do that. I always ask the question why, and why not that. So when we came to the geometry, everything made a little more sense. So I will discuss the geometry a little bit. So S is a 2n dimensional symplectic manifold. Ts is the velocity phase space. It is also the tangent space of S. And its elements are these canonical velocities, qi dots. T star S is the momentum phase space. It's kind of a review for people who have not really worked with the geometry of things. Also, the cotangent space. So, if you think of tangent space as housing vectors, then cotangent space houses linear functionals, or one differential forms. So pi, and that's exactly why, if you've been paying attention, I use the lowercase indices for p's and the uppercase for the qi dots. And f can be seen as a Legendre transformation, which is, if you remember, is pi qi dot minus curly L. Mathematicians like to call, so what I've bracketed is the mathematical terms. So mathematicians like to call it the fiber derivative. F or FL of TS gives us a subset of T star S. It will be the entire T star S if the Legendre transformation is invertible. In a general case, it will just be an improper subset. Okay, so this was some terminology. Now, what's important is noticing what these primary constraints do. So, phi m define a primary constraint surface. Call it gamma sub p. And then you can see by extension that F inverse of gamma sub p is a manifold of dimension n. So what this did was it sort of took the gamma sub p and placed it back in the tangent space, and this becomes a manifold of dimension m. You can check with the formal definitions of a manifold, but I'm just writing this for now. Definition. We're going to need this notion quite a lot. The function f q comma p defined in a neighborhood of gamma sub p is weakly zero. Anyone who's taken distribution theory will know the importance of weak and strong. But in any case, it's not surprising that Dirac was involved with this thing as well. Is zero. So F restricted to gamma sub p is zero, which you can denote as F is weakly zero, and strongly zero if F restricted to gamma sub p is zero, and that's not all. We need the gradients to be zero as well. So F with respect to qi and F with respect to the pi is zero, restricted to gamma sub p is zero. Okay, lemma. We need this lemma. F is weakly zero. That implies F minus Fm phi m is strongly zero, and gradient of F is weakly Fm gradient x phi m for some function Fm. I'm going to sketch the proof. So the step is to choose independent phi m as coordinates of a regular coordinate system denoted by x, which is an ordered or a product of phi and x tilde. X tilde are coordinates on gamma sub p, and phi are the coordinates that we mentioned before in neighborhood of gamma sub p. So F is weakly zero. This means that F at zero and x tilde is zero because on the constraint surface phi will be zero. F of phi comma x tilde can be denoted as integral from 0 to 1 d over d tau f of tau phi comma x tilde d tau, fundamental theorem of calculus. So this means we can use all our properties, all our rules, and we get and then F is then Fm phi m, with phi m as Fm as the top thing there. Now what we'll do is open sets we can have open sets ui of gamma sub p such that phi m is zero, where the lemma applies. Else on vk, where phi k is non-zero, just choose f as f divided by phi k times phi k, and then finally using locally finite partition of unity, so that wherever they overlap, they have the same value. So same value on overlap. We can extend entirely to give a theorem. Theorem 1. If f vanishes on gamma sub p, then in a neighborhood of gamma sub p, f is fm phi m for some phi m. And I'm just going to state theorem 2. Trust me, this might sound a little dry right now, but we're going to really need these theorems. So lambda I qi plus mu I delta pi is 0 for where arbitrary variations, where these guys are arbitrary variations. Tangent gamma sub p, then lambda I is um phi m, and mu I is um partial phi m partial pi. Yeah, I should have used a higher index here rather than. Yeah, I'll fix it later. So again, a sketch of the proof is, this will be a quick one. At a given point x on gamma sub p, a basis of the tangent space, so tx gamma sub p, with gradient at x of phi m, form a basis of tx of gamma, which is the entire phase space, and that means this pair of lambda comma mu is orthogonal to tx gamma sub p. Hence, it must be a linear combination of the gradients of phi. That's the entire point of this proof. But anyway, enough of the uninspired mathematics. It's time to move on to generalized Legendre transformations, and that's where we're really going to use these a lot. Generalized Legendre transformation. So first we have Hamiltonian as qi dot pi minus L, with the fiber derivative as a map from Ts, the velocity phase space, the gamma sub p. Uh, Delta H is then going to be qi dot delta pi delta qi dot pi minus, so I'm just varying the Lagrangian each dependence at a time, and this gives us some terms will cancel off. So this means that this Hamiltonian is a function of p and q, since delta p is seen as linear combination of delta q and delta qi dot. That means that q, delta p and delta q are tangent to gamma sub p, and moreover H Hamiltonian is defined on gamma sub p only. Now we wish to extend to the entire phase space. To obtain canonical equations. No other reason why. So what I'm gonna do is I'm gonna just write this what we had before on this page. I'm just gonna write it in a better way. So now we apply theorem 2, because we have an expression that looks like it can be used in theorem 2. So qi dot minus partial h with respect to pi is weakly, I believe was the expression in the theorem. and minus is weakly so that means qi dot, if we want to remove the weak symbol, we'll simply have to restrict it to gamma sub p plus partial phi m with respect to pi restricted to gamma sub p, and minus partial L with respect to qi partial h with respect to qi restricted to gamma sub p plus partial phi m with respect to qi restricted to gamma sub p. And then we have a sort of a transformation going on here, a transformation law. qi it can be written as a function of x tilde and u, and then qi dot can be written as function of q comma p, because it's the entire phase space now. So this is a map from cotangent space to tangent space. And just for the sake of completion, pi, which is this, and a function of q and q dot, and which is a function of, it can be written as a function of q and q dot, are maps from tangent space to cotangent space. This is all too abstract, but I will give examples later on. So, but finally, by theorem 1, h tilde can be written as h tilde plus phi m function of q and p qi dot then just becomes the following. Pi dot is minus phi m should please. So this what we've achieved here with the qi dot and the pi dot, or more explicitly the Hamiltonian, writing the Hamiltonian as a linear combination of constraints. Maybe I should have another multiplier here. Yeah, I think I should call that cm. We left that out, my bad. So this is akin to the Lagrange multipliers procedure from multivariable calculus. And the Hamiltonian that we have here can be called the phase space Hamiltonian. So h plus phi m. H was defined on gamma sub p, and this extension is in the neighborhoods of gamma sub p. So this really is a fitting extension, and the theorem that we've sketched the proof of before guarantees that it is. So There's two ways of writing. You can keep the weak symbol, and then you don't need to restrict any of it because that's what the weak means. Or you can remove the weak, like I had removed here, back here, and but you need to restrict it to the gamma sub p. Okay, so the new equations of motion from what we did so far are going to be qi dot is weakly qi Poisson bracket with phase space Hamiltonian, which you can sort of decompose by definition of the phase space Hamiltonian. This is just by definition of the phase space Hamiltonian. So you can similarly do this with pi dot, the time evolution of the momentum, canonical momentum. And generally, you can do this with any function. Any function's time evolution or in this constraint setup can be described like, as a Poisson bracket with the phase space Hamiltonian, and then that decomposes into a Poisson bracket with the gamma sub p Hamiltonian and the phi m constraint extension. Now this all is fine. This gives us the setup for what is to come. This is still not enough. We need to outline uh, an even more foolproof algorithm, which is called the Dirac Bergman algorithm. A point q comma p on gamma sub p must remain there at later times. That's the entire point of it. So because the thing is, we got time evolution, which means we know how a point is going to evolve. But when it evolves, is it still on gamma sub p or has it escaped? That is one question we still haven't really answered. So phi m, that just means phi m must evolve just like q and p. An intuition for this is, say you have like some point which is on gamma sub p, say it evolves into something else, say it gets off gamma sub p, it will escape unless this plane itself evolves the same way, so that it sort of gets under these evolved points. That's the entire intuition. So then this is the constraint, the primary constraint plane. So this is phi m at some later time equals 0. If it evolves the same way as those points, those q comma p points, that's when the points are still going to remain in the gamma sub p. That's kind of a small rough sketch to why we should do something like this. So phi m dot must evolve just like q and p, which means it needs to go in the time evolution equation. It needs to satisfy it, otherwise it won't evolve quite the same way. So phi m and then phi n un. Just plug it in the, the dynamical equations we had, which we can denote as HM plus CMN UN set to 0 if the determinant of C is non-zero, then you can invert the equation. So UN will be weakly equal to minus CNM, where the raised indices denote the inverse, HM. And then any evolution of any observable will be Poisson bracket with H plus, rather a minus, F Poisson bracket with M CMN phi n Poisson bracket with F, because we could solve for the multiplier UN. This is, a really good case. We like this. It really helps simplify lots of things. Other case is if the determinant is 0, then these lead to certain K1 number of new constraints. That's right. Just when we thought we couldn't get enough of the constraints, we have more. So phi k is weakly 0. Those are the k constraint. J1. Yeah, sure. Okay, I'll call them K1. M plus 1, M plus K1, which we can call J1, new constraints, are called secondary constraints. Primary came about from the Hessian itself. The secondaries are coming from the consistency, which means that we want the time evolution to remain on gamma sub p. That's consistency. We want that. That's why we have secondary constraints popping up. Now, gamma j, weakly 0 for j is 1 to j1. Define a submanifold gamma sub 1 of gamma sub p. Applying consistency again, since we have constraints, we need to see if they are consistent. I mean the secondary constraints. We get a similar sort of setup. Which we can call Hj and Cjn un set to 0, but on gamma sub 1. Now, depending on the determinant of Cjn, we may get tertiary constraints, and we basically keep doing this process until we reach a start point. Either the determinant is non-zero or it's just trivially satisfied. So repeat algorithm, that's why it's an algorithm. We need to keep repeat algorithm until consistency is attained.